Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at approximating the solution to a system of nonlinear algebraic equations. So in this topic, we will describe real-valued functions of two and possibly more variables. We will describe tangent surfaces in 2 dimensions and discuss generalizations in higher dimensions. We will discuss the generalization of Taylor series. We will then discuss finding simultaneous roots of n expressions in n variables. So thus we will frame our root finding problem as one of finding a zero of a vector valued function of a vector variable. We will then introduce the one topic or one algorithm we will look at this course, and that is Newton's method in higher dimensions. Now let's recall Newton's method, a root finding algorithm. What we do is we convert a nonlinear algebraic expression into a linear problem. So at a point, we find the expression of the tangent line at that point. So that line is tangent to the curve at that point, assuming, of course, the curve is differentiable. Now, the tangent line is a single linear equation in a single unknown, and that's something that's quite easy to solve. Recall also that we will convert a nonlinear algebraic equation into a root finding problem. So suppose we are trying to solve this nonlinear algebraic equation. Rather than trying to solve for x and y in this form, what we will do is we will move everything to the left-hand side. This is now an expression in both x and y, and we are attempting to find a root of this expression. Now suppose we have a real valued function of 2 real variables. As we see here, this is the 0th order Bessel function evaluated at the distance the point is away from the origin. All right, and we can see that this is interesting shape. It looks like it's a water droplet in a pond, for example. Now, we are going to interpret this instead as a real valued function of a real 2-dimensional vector. So instead of thinking of it as a function of 2 variables, it's the function of a vector variable. Consequently, of course, you can see that we could have a function of a 3-dimensional vector or an n-dimensional vector. The primary requirement, however, is that it is a real valued function. Now, recall that in 1 dimension, that is a function of a 1-dimensional vector or just a function of a real variable, we can find a tangent line at any point. Similarly, given a differentiable function of a 2-dimensional vector variable, you can see in this image that, yeah, at more or less any point, you can probably find a tangent plane. So, of course, a tangent plane is one that touches the surface at one point and perhaps in neighboring points, but touching at one point and is parallel to the surface in all directions. In general, actually, given a differentiable function of an n-dimensional vector variable, we can actually find a tangent n-1 dimensional hyperplane at any point. So the thing is, the algebra takes care of this. We don't have to worry so much about it, but we can find it and then we can work with it. Now in 1 dimension, the tangent plane can be found as follows. Well, more or less taken entirely straight from the Taylor series. In 2 dimensions, the derivative is replaced by the gradient, and if we go down to 1 dimension, the gradient is just the derivative. So now f at u is equal to f evaluated at the point around which we are defining the tangent plane plus the gradient at that point inner producted with the distance of u, or the difference between u and u naught. And the gradient is just a vector, a 2-dimensional vector, the first entry of which is the partial derivative with respect to the first variable evaluated at u naught, and the second entry is the partial derivative with respect to the second variable, again evaluated at the point u naught. As you may expect in n dimensions, if we have a real valued function of an n-dimensional real valued vector variable, again, it's identical. It's the value of the function at u naught plus the gradient inner producted with the difference between u and u naught. Now, from linear algebra, you will recall that a linear equation in one variable is 0 at a point. A point is a 0-dimensional object. A linear equation in 2 variables is 0 along a line, assuming it has a 0. And in 3 dimensions, a linear equation in 3 variables is 0 along a surface. All right, well, it's the same for nonlinear functions, except the zeros tend to be along curves. So here we see the 0th order Bessel function as described before, and I have now drawn in the plane z is equal to 0. So this is where this function is 0, and you can see that this nonlinear function is 0, but not along straight lines, but along curves. So you can also imagine that this tends to be the case in higher dimensions. Now, suppose we add a second function. So in this case, we have 2 functions, one drawn in red, the other drawn in blue. The second function is sine at u1 minus cos at u2. At this point, you can see that the second function is also 0 along curves in the plane z is equal to 0. Right there, we can see a point where both functions are 0 simultaneously. However, these are nonlinear, so there may actually be multiple instances where both surfaces are simultaneously 0. And there's a third. So we would like to find such points. Now, one important point is that we will be doing this in n dimensions as well. Unfortunately, I cannot draw functions in n dimensions, but as you may suspect, a function of 3 variables is 0 along surfaces. If I have 2 functions of 3 variables, they may simultaneously be 0 along curved lines in R3, and consequently, if I have a third function of 3 variables, or a 3-dimensional vector, in this case, it is likely that it is sufficiently many constraints to have individual points where all 3 functions are simultaneously 0. Now, you'll recall from linear algebra, when we had a system of 2 linear equations in 2 unknowns, what we did is we wrote that not as 2 linear equations, but as a vector-valued function, that is a matrix times a vector of unknowns equaling a target vector, which we tried to solve for. Well, in this case, if we have two functions, let us think of these two functions not as f and g, but as components of a vector-valued function of a vector variable. So now we have two functions, f1 in red, f2 in blue. Therefore, we have f at u is equal to, well, the first value is the Bessel function, the zeroth order, evaluated at the distance from the zero vector, and the second is sine at u1 minus cos at u2. Well, we can now take any point in the R2, say 0, 0, and we can evaluate this vector-valued function at a vector variable, such as at the origin. So in this case, if we evaluate f at the origin, we get the values 1 and -1. But we are trying to find a simultaneous root. We want to find values of u such that f at u is the zero vector. Thus, we will have an n-dimensional vector-valued function of an n-dimensional vector variable. And we will denote this as a vector-valued function that is bold of a vector variable u. So for example, f at u may be this vector-valued function here. Now, this is a non-linear function because, again, you have products of u1 and u3, or u1 and u2. We want to find all values, or perhaps just one value, of u such that this function evaluated at that point u is equal to 0. Now, for this particular case, you will see that if the argument u is the zero vector, then the right-hand side is all zeros. So one simultaneous root of these three nonlinear expressions is just when all three variables are 0. However, if this was a linear equation, we would know that this is a unique solution, but these are nonlinear. So in this case, there are actually two other simultaneous roots. For example, if we were to substitute u1 and u2 equaling 6 root 2 and u3 being 27, then all three expressions would simultaneously be 0. And at the same time, if we were to substitute u1, u2, and u3 being these three values, again, all three expressions would simultaneously be 0. For every other vector-valued argument of this function f, at least one of the expressions will be non-zero. So in this case, we happen to have three simultaneous roots of this three-dimensional vector-valued function of a three-dimensional vector variable. Now, some of you keeners may have noticed that if we are trying to find a simultaneous zero of this vector-valued expression, we can rewrite this by moving u1, u2, and u3 from each of the three expressions to the left-hand side. This should look familiar. So if we now define g of u being the right-hand side of that new expression, then solving f at u is equal to the 0 vector is the same as solving g of u is equal to u. And so we could, in theory, apply fixed point iteration. So thus we could start with an initial guess u0, and then evaluate this new function g at u0 to give u1, then evaluate u1 at g to give u2, and so on and so forth, and hopefully this converges. Unfortunately, if you do not start at a root, this fixed point iteration does not converge for any initial u naught. So this is not going to work here. However, if you noted this, hey, kudos to you. Now, in most cases, we will not be able to solve f at u equaling the 0 vector exactly. Instead, what we're going to do is we're going to start out with an approximation. Hopefully we have an initial guess as to the simultaneous root such that when f is evaluated at this initial guess, it's close to 0, or the 0 vector. Then, like we did with a real valued function of a real variable, we are going to devise a Newton-like method, but now for higher dimensions. So that will be the one topic in this particular subsection. So what we're going to do is we're going to find a sequence of vectors. This is an iterative technique where hopefully the 2 norm of the value of the function evaluated at the next point is less than the value, the 2 norm of the function evaluated at the first point. And then we will find a third point, hopefully where this 2 has a smaller 2 norm. And hopefully this continues to go on. So, just like Newton's method, where we found a sequence of approximations of the root, this sequence converged to the root if in the limit the absolute value of the function evaluated at this sequence of points tends to 0. At least theoretically. Of course, numerically that never happens, but theoretically. Well, we are also going to hope that this sequence of vectors u, such that when we evaluate the function at this sequence of vectors, the 2 norms of these also go to 0. So the value of the function at these vectors gets closer and closer to the 0 vector, and thus closer and closer to a simultaneous root of this vector valued function of a vector variable. Following this topic, you are now aware that differentiable functions of 2 variables which are smooth have tangent planes. You know that, as with linear equations, we require n expressions in n variables if we want to find simultaneous roots. You know that we will be expressing such n functions of n variables as a vector valued function of a vector variable. And we want to find a simultaneous root for all of the entries in the vector. That is, we want to find values of x or u such that f evaluated at that vector u produces the 0 vector. And you are aware that in this subsection we are simply going to look at one technique, which is a Newton-like method, but one that works in higher dimensions. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!